This is section 9.1, and what we're doing in 9.1 is we're doing hypothesis testing, but instead of just a single variable or two variables, we're now doing hypothesis testing with many variables. In previous chapters, hypothesis testing with two variables involved a single parameter, either the mean or the proportion, and a binomial distribution of data. And so in this chapter, what we're going to do is we're going to explore hypothesis testing with two variables, but instead of having a binomial distribution of those variables, yes or no, the variables can have multinomial distribution. In other words, a lot of different categories. So just to show you really quick what we're talking about, we'll zip down to the example problem. This example problem, this is the category 1. So we'll say category maybe A, and this is category B. Now this is a type of problem we couldn't do before because we didn't have the mathematics to do this. Notice category A has two options, male or female, and category B has 4 options. So what this describes is a sample where they surveyed random people and they said male or female, and then what is your highest level of education? So for example, this 60 represents 60 people that surveyed responded that they were male and their highest level of education was high school. Okay, this number represents 44 of the participants who indicated that they were female and their highest level of education was a bachelor's degree. So we couldn't do this type of problem before because we were limited to just binomial type things, A or B, on or off. Either you met the requirement or you didn't meet it. Proportions, P and Q, right? That kind of stuff. And so now with this type of hypothesis testing, we're going to be able to look at more complicated data sets. Okay, and so what we're going to be doing is comparing two frequencies. The first is the observed frequency, and this is what we collect during the experiment. The second type of frequency is the expected frequency, and this is theoretical. This is our theoretical frequency, what we expect the distribution to look like. And what we're going to do is we're going to compare the theoretical or the expected frequency to the observed frequency. And then we're going to make a conclusion about how well the expected frequency matches the observed frequency. So to do that, this is our calculation. So in order to find the probability of the expected frequency, what we do is we take the row total, multiply by the column total, and then divide by the total. So this is how we find the expected frequency. If the observed frequency and the expected frequency are the same, then the variables are independent. And this is why this is called the chi-square test for independence. We're checking to see, are the variables, the two variables that we're looking at, gender and highest education level, are they independent or are they dependent on each other? If the observed frequency and the expected frequency are different, then they are not independent. They are dependent on each other. And so our null hypothesis is going to be that the two variables are independent, that there's no relation between the two variables. The alternative hypothesis is that they are not independent, that they are dependent. Okay? And so that's the setup of what we're going to look at. So how do we calculate a test statistic for this? How do we do a test statistic? Are we looking for a z-score or a t-score? And the answer is we're looking for none of the above because they don't apply to this type of a scenario. Instead, what we need is a new test statistic called the chi-square test for independence. Test for independence because we're testing to see if the two variables are independent. Chi-squared because that is our test statistic. And by the way, this is called chi K-A-I, like Cobra Kai, not Chi. So sometimes students pronounce this as chi squared, and it's actually chi squared. So how do you set up the experiment? First, state your null hypothesis. The variables are independent. Our alternative is that they are not independent, that they're dependent. Make sure that we have a random sample taken and that all the expected frequencies are greater than or equal to 5. So all of your expected frequencies have to be greater than 5. Then we're going to calculate chi squared. And so how do we calculate chi squared? This might look a little bit familiar. What you're going to do is you're going to take your observed frequency for a category, subtract the expected frequency, square it, and then divide by that expected frequency. We've done a calculation like this before. This is similar to the standard deviation calculation that we did. And then you're going to add them all up. And that is chi squared. And we'll show you this in the tech tool. The graph of chi squared is not a normal distribution. The graph of chi squared looks like this. And as a matter of fact, I actually have the graph of chi squared. This is chi squared. And the graph of chi squared, you notice it doesn't go negative. We're only looking at the positive value of chi squared. And we always look at area to the right. We're always looking at area above chi squared. So these values along here, 2, 4, 6, 8, and maybe I can zoom in a little bit on those. These values, 2, 4, 6, 8, I think I zoomed in too much. These are the values of chi squared. Okay, so these are the values of chi squared. The distribution of chi squared is greatly dependent on degrees of freedom. Watch this. 2, 3, 4, 5, 6, 7. You see how that curve changes? It's almost like a tsunami. Like it's coming in and then the wave gets really big right there. But the area under that curve changes tremendously based on your degrees of freedom. So degrees of freedom are extremely important in chi squared, in calculating a chi squared distribution. And so in this situation, this is the chi squared is equal to 5. Our upper bound is 100, and then here is the area under that curve. But this gives you a visualization of how the degrees of freedom impact the shape of chi squared distribution. So since degrees are so important, how do you calculate the degrees of freedom? So you take the number of rows, minus 1, times the number of columns, minus 1. So remember, your data set is not going to be a simple 2 or 3 row or column situation. You're going to have lots of rows and lots of columns with lots of data in them. And so you take the number of rows, minus 1, times the number of columns, minus 1, and that is your degrees of freedom. Okay? Then once you have that chi squared, you either go to a website, or you go to Desmos, or you go to Google Sheets, and you calculate the area under that curve. And that's what this chi-dist does. And we'll show you how this works in a little bit. Once you have that area, that is your p-value. So this will give you a p-value. You compare that p-value to your threshold of alpha, and you either reject or you fail to reject the null hypothesis, and then you state your conclusion. So this should be very familiar. You should be like very familiar with, okay, I'm going to get a p-value, I'm going to compare it, I'm going to accept or reject. The new part, the new tricky part, is the chi-squared stuff, okay, and how this calculation happens. So let's go through an example. So here's the example that we talked about a little bit earlier. So a random sample of 394 people were surveyed, and each person was asked to report their gender, male or female, and their highest education level, high school, bachelor's, master's, or PhD. And what we'd like to know is, are the variables independent? In other words, does your gender impact the highest education level that you attain? So our null hypothesis is that the variables are independent. that there is no correlation. There's no reason to think that gender and education level are related to each other, that they're completely independent. That's the null hypothesis. The alternative hypothesis is that they're not independent, that your gender does influence the highest education level that you attain. And we want to test this at a 1% threshold, okay? So we're going to state that the assumptions are met. So was it a random survey? Yep, it was random. And do the expected frequencies all have values greater than 5? So if we go up here and we check all of these frequencies right here, are they all greater than 5? Yeah, they're all greater than 5. Okay, great. So that means we've met the conditions to move forward with our calculations. So here is how we calculate expected values. Now remember, the table that we have is the observed values. These are our observations. These are all our observed values. We now need to calculate the expected, the theoretical value. And the way we do that is cell by cell. So we're going to start right here with male high school. So what we do is we take the total males and the total high school. So the row total goes here. The column total goes here. We divide by the total. And we get a value of 50.89. So that is our theoretical expected value. We then go to the next cell. So we'll go to male bachelors. And so we take 201, we multiply it by 98, and then we divide that by 395. So you take the row total, you multiply by the column total, and then you divide that product by the total. And that is 49.87. 49.87. And we do this for every cell. So for every cell, we take the row total for this cell right here. We're going to take the row total, the column total, multiply those two together, and then divide by the total, and we'll get a value. And so this is going to create a table of expected values, of theoretical values. So we did this for every cell. So here are the observed frequencies. These are the measurements that we got when we went out and surveyed everyone, okay? Based on those observations, this is the calculation of our expected frequency. And this again is where we took the row total, multiplied by the column total, and divided by the total. And we did that for every single cell, okay? Now we can calculate chi-squared. So we take the difference of our observed and our expected. So you subtract these two numbers. Then you square that value, and then you divide that squared value by the expected, by the theoretical, and that gives you this number. It kind of feels like the difference from the mean squared. Remember when we were doing standard deviation? It's kind of like that. You're subtracting, you're finding the difference between the two, you're squaring it, but then you're dividing by the expected. And then what you do is you add these all up. And that is chi-squared. This is your test statistic. This is the value on that crazy looking graph that we just had that you're going to plot 8.0061 and find the area above. That is chi-squared. So now we have chi-squared. We also need to know our degrees of freedom. So we have, in this situation, we had 2 rows, so 2 minus 1, and we had 4 columns, 4 minus 1. So that's 1 times 3. So our degrees of freedom are 3. So let's synthesize this. Here's the p-value. That's chi-squared. Here's our degrees of freedom. We just did that. Doing this all in a Google Sheet looks something like this. And so here's all the calculations in a Google Sheet. This is the sum of all of these values. So this is chi-squared. And then if you use the formula chi-dist, you have to put in chi-squared followed by the degrees of freedom. So this is chi-squared, and this is your degrees of freedom. And it will give you the area right away. So 0.0459. This is how you do it in Desmos. And again, here is the area from Desmos. So two ways of finding this area. Most of the time you're going to be using Google Sheets to do this. And so this is our p-value. Our p-value is much larger than our threshold of 1%. So remember, our threshold was 1%. Our p-value came in at 4.58%. And so that means we fail to reject the null hypothesis. Therefore, the variables are independent, which means gender does not influence your highest education level. What we have here are a collection of data points, and one thing I might want to know is what is the sum of these data points. So there's the sum, 77, and there's 5 of them. And we're told that all 5 are equally likely to happen. So if I have, like, for example, a 5-sided dice, and I roll it, how many A's would I expect to come up? How many B's would I expect? How many C's, given that I rolled it 77 times? Well, you would take 77, this value, and divide it by 5. And so I would expect that there would be 15.4 A's and 15.4 B's. So I would expect 15.4 of each one if they're equally distributed. So we may ask, is this a fair dice? If we roll it 77 times and there's 5 different categories, we would expect each category to come up about 15.4 times. And clearly, our observed frequencies don't match that. So let's calculate chi-squared. So in this cell, what we're going to do is we're going to say this equals, and this is what you're going to have to do, right? You're going to have to know how to do these calculations. We're going to take the observed frequency and we're going to subtract the expected frequency. We're going to find the difference between those two. This is the formula that we have. Then we're going to square it. So that's the value squared. And now we're going to divide that whole thing by the expected frequency. The expected, not the observed, the expected. And so there is this is called the Pearson residual for category A. And we're going to do the same thing for category B. And so all we got to do is fill this down. There you go. And so now we've done all those calculations. Thank goodness for spreadsheets, right? And now we want to add these up. So we want to say equals sum. Add up all these residuals. And that is chi-squared. In the next problem, you'll notice that these categories are not equally distributed. You'll notice that they have a probability. The probability of A is 0.1. The probability of B is 0.4, 0.2, 0.3. So again, what I'll do is I'm going to highlight this whole thing. I'm going to copy it, paste it right here. So there it is. And I want to find the sum equals sum of all of these. So there's the sum, 92. Now I've got 92 items. Back in the beginning, I'm told that 10% of them are in category A, 4% are in category B, 2% are in category C, or 20%, pardon me, and 30% are in category D. So 10, 40, 20, 30. So if I go back here, my expected frequency of these 92, I would expect 92 times 10%, 0.1. So if 10% of my values should be in category A, my expected frequency would be 9.2. The observed frequency is 17. That's a big difference. In category B equals 92 times, category B was 40%, so 0.4. So I would expect 36 of the 92 to be in category B. Category C, what was category C? 20%. So that would be equals 92 times 0.2. And category E should equal 92 times 0.3. So these are my expected frequencies based on the distribution that the problem gave me. Now I have my observed frequency, I have my expected frequency, and now I can calculate the squared residual. So this is the same calculation I did before. So I'm going to say equals, I'm going to take the observed and subtract the expected. I'm going to square that number and divide it by the expected. And there's my squared residual. I'm going to do this for all 4 rows, and then I'm going to add them all up. And there is chi-squared.